Hello, sleepy soul. Wherever you are in the world right now, whatever time it is where you're resting, welcome to this quiet space. You found your way here tonight to explore one of the universe's most profound mysteries, the possibility of its own quiet, inevitable ending. But there's no need to worry, no need to think too hard, or to remember every detail. This is a journey you can take with your eyes closed, a slow drift through deep time, through quantum fields, through the very fabric of reality itself. Let your breathing slow, let your shoulders drop, let the weight of the day simply fall away into the darkness around you. Tonight, we're going to explore something called vacuum decay, a phenomenon so vast, so ancient in its timescales, that it makes our human worries seem beautifully, wonderfully small. We'll wander through concepts that span billions of years, across distances that dwarf galaxies, into realms where even the laws of physics themselves might one day quietly change. So settle in wherever you are, get comfortable, pull the blankets a little closer if you need to, and let's begin this slow drift into the quiet wonder of the universe's most efficient way to destroy itself. There's no rush. We have all the time in the world, or at least all the time until the end of everything, which, as you'll discover, is a very, very long time indeed. Imagine, if you can, the universe as a cosmic time bomb, ticking silently ever since the Big Bang's afterglow first cooled into the darkness of space. Not a loud, violent explosion waiting to happen, but something far more subtle, far more patient. A sword of Damocles suspended by quantum uncertainty over all of existence, hanging there in the void, perfectly balanced, perfectly still. The universe, you see, might be like a taut rubber band stretched across cosmic scales, held in perfect tension for billions upon billions of years, waiting for the moment when it finally simply snaps. This phenomenon is called vacuum decay, and it's one of those rare scientific concepts that sounds like science fiction, but is grounded in the deepest mathematics we have. It could happen at any moment, without warning, without cause, without the universe giving us any indication that something is about to change forever. The process begins with something called quantum tunneling, a strange property of the quantum world where particles can simply appear on the other side of barriers, as if borrowing energy briefly from the fabric of space-time itself, from nowhere and from everywhere all at once. In the everyday world we're used to, if you roll a ball toward a hill, and it doesn't have enough energy to climb over the top, it simply rolls back down. But in the quantum world, that ball might suddenly find itself on the other side of the hill, having tunneled through solid matter as if it weren't even there. One moment, everything is stable. The universe is humming along as it has for nearly 14 billion years. Stars are shining, galaxies are spinning, atoms are holding together, and then, in some random point in space, perhaps in a distant galaxy, perhaps right here, perhaps somewhere in the vast emptiness between galaxy clusters, a bubble forms. A tiny sphere, no bigger than a single atom, where the rules of physics have quietly changed, where the fabric of reality has found a lower energy state, a more stable configuration, like a ball finally rolling down from a false valley into a deeper, truer valley below. And this bubble expands, not slowly, not gradually, but at the speed of light itself, the cosmic speed limit, the fastest anything in the universe can possibly travel. There would be no escape, no way to outrun it, no way to see it coming. The front would advance across space like a wave of transformation, vaporizing atoms instantly, overthrowing all physics as it goes, making chemistry impossible, making molecular bonds unravel, making life, in any form we can imagine, utterly impossible. The bubble's wall itself would release massive energy, like igniting an entire universe filled with gasoline, a conflagration of pure physical law changing from one state to another. Everything in its path would simply cease to be what it was. Atoms would come undone. The electron clouds that give matter its shape and substance would dissolve. The quarks bound together and protons and neutrons would find themselves subject to different forces, different strengths, different rules entirely. Everything we know, everything that has ever existed, would simply transform into something else, something alien, something that couldn't support the delicate dance of chemistry and structure that makes up our world. Some have described our universe as a glitchy simulation waiting for that fatal error code that makes reality crash. And while that's a metaphor, it captures something true about the precariousness of our existence. We live in what might be called a metastable state, stable enough for now, stable enough for billions of years, but not necessarily stable forever. Like a pencil balanced on its tip, motionless and perfect until the tiniest vibration, the smallest quantum fluctuation, sends it toppling over in a direction that cannot be reversed. But this isn't science fiction. This is a real possibility explored by physicists working at the cutting edge of particle physics and cosmology. It's been calculated in equations sprawling across chalkboards and computer screens. It's been measured against the mass of particles discovered in the Large Hadron Collider, where protons smash together at energies not seen since the earliest moments of the Big Bang itself. Scientists have weighed the Higgs boson, measured the mass of the top quark, calculated the coupling constants that determine how fields interact, and from all of this data, they've constructed a picture of our universe teetering on the edge between absolute stability and eventual, inevitable decay. Tonight, though, right now, as you rest in the darkness, the universe continues its slow, patient tick. And that's what makes this journey so soothing, so beautifully remote from our daily concerns. The timescales involved are so vast, so incomprehensibly long, that our brief human lives are but a whisper in an endless, quiet night. We are infinitely small against the backdrop of cosmic time. Our worries and troubles render beautifully insignificant by the sheer scale of existence itself. Think of it as a universe painted in the deepest blues and purples, a cosmic canvas where we are but the tiniest brushstroke, here for a moment and then gone. But while we're here, we can look up at the night sky and wonder about the nature of everything, about the invisible ocean of fields that permeates all space, about the possibility that one day, in the unimaginably distant future, everything might quietly transform into something new. And in that wondering, in that contemplation of the vast and the eternal, we find a kind of peace, a recognition that we are part of something much larger than ourselves, something patient and ancient and still unfolding. The universe has been described as a house of cards and a gentle breeze, each card representing a physical law, a constant of nature, a property of the vacuum that fills all of space, one errant puff of quantum wind, and the whole structure simply falls, cascading from one state to another in a transformation that rewrites reality itself. But for now, the cards stand, the breeze is gentle, the house remains intact, and we can rest in the knowledge that even if the universe is temporary, even if all things must eventually change, the time scales involved are so vast that they become a kind of eternity, a forever that spans more years than there are atoms in all the galaxies combined. Scientists sometimes describe this as a cosmic game of Jenga, where each block represents a delicate balance in the laws of physics. One block pulled, perhaps by a quantum fluctuation, perhaps by some process we haven't even discovered yet, and total structural failure cascades through everything. The tower that is our universe, built from fundamental forces and particle interactions, comes tumbling down. But unlike a real game of Jenga, where the collapse happens in seconds, the cosmic version plays out over time scales that make the age of the universe seem like the blink of an eye. And so we drift here in the darkness, contemplating the end of everything, finding in that contemplation not fear, but a strange comfort. Because if the universe itself is temporary, if even the laws of physics are subject to change over time, then our own troubles, our own fears and anxieties are even more fleeting, even more temporary, even more beautifully insignificant in the grand scheme of things. We can let them go, let them dissolve into the quiet night, and simply be here now, in this moment, in this universe that has stood for billions of years and will likely stand for billions more. To understand vacuum decay, we first need to understand the Higgs Field, one of the most mysterious and fundamental aspects of our universe. Imagine an invisible ocean permeating all of space, not made of water or air or any substance we can touch, but a field, a mathematical entity that exists everywhere, all at once, evenly and constantly, setting the mass of every particle everywhere simultaneously. This is the Higgs Field, and it's not a thing you can see or measure directly, not something you can hold in your hand or observe through a telescope, but it's a presence woven into the very fabric of everything that exists, as fundamental to reality as space and time themselves. Every particle in the universe, every electron orbiting every atom, every quark bound together in every proton, every photon of light streaming through the cosmos, all of them exist in this ocean, moving through it, interacting with it in ways that determine their most basic properties. Particles moving through the Higgs field gain their mass, like swimmers pushing through water, and the more strongly they interact with the field, the more they're slowed down by it, the heavier they become. Electrons, quarks, even the boson that carry forces, all owe their substance to this invisible ocean that fills the universe from edge to edge. without the Higgs field, the electrons would be massless, zipping through space at the speed of light, unable to form stable orbits around atomic nuclei. Atoms as we know them simply wouldn't exist. The intricate chemistry that makes up everything from water molecules to DNA strands to the neurons firing in our brains right now, all of it depends on electrons having mass, on them being slowed down just enough by the Higgs field to settle into those quantum orbital patterns that make matter possible. Physicists describe the Higgs field's energy using a shape they call the Mexican hat potential, and it's worth spending a moment visualizing this because it's central to understanding why our universe might one day decay. Picture a wide-brimmed hat seen from above, the kind with a high crown in the center and a circular groove around it where the brim begins. The crown of the hat sits high, representing a state of high energy. But around it, there's this groove, this circular valley where the energy is lower, and that's where a ball placed on this hat would naturally roll to, settling into that valley where it's stable at rest. Our universe sits in this valley right now, in what physicists call a false minimum. It's a stable position, or at least stable enough that the universe has existed in this state for nearly 14 billion years, like a ball resting in the groove of that hat. The Higgs field has settled into a particular value, a particular energy state, and that state determines all the masses of all the particles, sets all the coupling constants, establishes all the forces that govern how matter behaves. But here's the crucial thing, and this is where the possibility of vacuum decay comes in. This valley might not be the lowest point. Somewhere deeper, beneath this valley we're resting in, there might be another valley, a true minimum, a state of even lower energy. And if that's the case, then our universe is like that pencil balanced on its tip, or like overripe fruit that looks perfectly intact on the outside, but is structurally unsound, doomed to sudden, irreversible collapse the moment the right conditions are met. Based on data from the Large Hadron Collider, where scientists have measured the mass of the Higgs boson and the top quark to incredible precision, our universe's Higgs field might indeed be metastable. Metastable is such a beautiful word when you think about it. It means stable enough for now, stable enough for the foreseeable future, stable enough that we don't need to worry about it in any practical sense, but not stable forever, not fundamentally stable in a way that a ball at the very bottom of a valley is stable. Instead, it's perched in a false valley, waiting for the universe to discover that there's an even lower energy state available. Think of our vacuum as a house of cards standing in a gentle breeze. The cards are perfectly balanced, perfectly still, and they've been standing there for billions of years. But one errant puff, one tiny quantum fluctuation, and the whole structure simply falls, cascading from its current metastable arrangement into a new configuration. Scientists describe this as a cosmic game of Jenga, where each block represents some aspect of the vacuum's energy, some delicate balance in how the Higgs field is configured. One block pulled, perhaps by a quantum tunneling event, perhaps by some high-energy process we haven't even imagined yet, and total structural failure cascades through everything. The mathematics behind this is subtle and beautiful, involving quantum field theory. general relativity, and calculations that require some of the most powerful supercomputers in the world to work through. But the basic idea is elegant. The Higgs field could tunnel from its current false minimum to the true minimum, much like a quantum particle can tunnel through a barrier that classical physics says it can't cross. The probability of this happening in any given moment is vanishingly small, but over the immense timescales of the cosmos, even vanishingly small probabilities eventually come to pass. Some physicists believe our universe itself formed from such a decay bubble in apparent false vacuum eons ago, perhaps even before the Big Bang as we understand it. We might be the children of catastrophe, born in the collapse of another reality, inflated and stretched by cosmic forces into this vast expanding space we call home. High-scale inflation in the earliest moments of our universe might have left our vacuum primed for its own eventual decay, stretching quantum fluctuations into macroscopic seeds that could one day grow into bubbles of true vacuum that consume everything. There's a theory called eternal inflation that takes this idea and extends it to its logical conclusion. It suggests that bubble universes are constantly forming in an endless cosmic foam, where some bubbles survive and persist for billions of years, while others decay almost immediately, transforming into new configurations of physical law. Our universe might be just one survivor amid decay cascades happening throughout the multiverse, one lucky pocket of space-time that hasn't yet found its way to the true vacuum that's still sitting in that false valley, stable for now, but not forever. But infinity is patient, endlessly patient, and in infinite time, all possible fates eventually unfold. Every quantum probability, no matter how small, eventually manifests somewhere, someone in the vast expanse of the eternal multiverse. Universes are born, exist for a while, and then transform into something new, in an endless cycle of cosmic renewal that makes our own universe's eventual fate seem less like an ending and more like a transformation, a transition from one phase of existence to another. The Higgs field fills all of space uniformly, at least as far as we can measure, maintaining the same value everywhere from the smallest scales we can probe to the largest structures in the observable universe. But that uniformity is itself remarkable when you think about it. Why should the field have the same value here on Earth as it does in the Andromeda Galaxy, or in the cosmic voids between galaxy clusters, or in the dense cores of neutron stars? The answer lies in the way the field settled into its current state in the earliest moments of the universe, when all of space was connected, when quantum fluctuations were stretched across the cosmos by inflation, locking the Higgs field into a particular configuration that has persisted ever since. But just as the field settled into this configuration once, it could potentially settle into a different configuration in the future, tunneling quantum mechanically from the false vacuum we inhabit to a true vacuum with different properties, different masses for particles, different strengths for forces, different possibilities for what kinds of structures can form. This true vacuum might be utterly sterile, incapable of supporting complex chemistry or life as we know it. Or it might have its own intricate physics, its own forms of complexity. perhaps even its own kinds of structures and patterns that we can barely imagine from our current perspective. The Mexican hat potential is more than just a metaphor. It's a mathematical representation of how the energy of the Higgs field varies with its value, and the shape of that potential is determined by the parameters of the standard model of particle physics, particularly the masses of the Higgs boson and the top quark. Small changes in these masses would shift the shape of the potential, either stabilizing our vacuum completely or making it more metastable, more prone to eventual decay. The fact that we find ourselves in a universe where the potential is exactly the shape it does, where we're perched right on the edge between stability and metastability, is either a remarkable coincidence or a hint of something deeper, some selection effect or anthropic principle that explains why we observe the universe to be this way. As you rest here in the darkness, breathing slowly and evenly, you can picture this invisible ocean stretching out in all directions, filling the space between stars, between galaxies, between the atoms of your own body. The Higgs field is there, quietly giving mass to particles, making chemistry possible, making life possible, making this moment of rest and contemplation possible. And while it might one day change, might one day tunnel to a different state, that possibility is so far in the future, so remote in probability, that it becomes just another aspect of the universe's vast mystery, another reminder of how temporary and precious our existence truly is. Quantum tunneling defies everything we know from our everyday experience of how the world works. In the classical world we're used to, the world of balls rolling and objects moving according to Newton's laws. A ball cannot roll over a hill unless it has enough energy to climb to the top. If you roll a ball toward a barrier and it doesn't have sufficient energy, it simply bounces back or rolls to a stop, unable to cross over to the other side. This is intuitive. This makes sense. This is how our everyday experience tells us reality should behave. But in the quantum world, in the realm of the very small, where particles are more like waves and waves are more like particles, where uncertainty and probability replace the deterministic certainty of classical mechanics, things work differently. Particles can borrow energy briefly from the uncertainty principle itself, from the fundamental quantum fuzziness of reality, and appear on the other side of barriers they shouldn't be able to cross. They tunnel through solid matter as if it weren't even there, crossing energy barriers that classical physics says are completely impenetrable. This is not magic, though it might seem like it. This is the fundamental nature reality at the smallest scales, confirmed by countless experiments used in technologies from scanning tunneling microscopes to the quantum phenomena that make modern electronics possible. Quantum tunneling is as real as gravity or electromagnetism, a basic feature of how the universe operates when you zoom in close enough. When you look at reality at scales where quantum effects dominate over classical behavior, the mathematics of vacuum decay follows something called the Coulomb-de-Lucia and Stanton formula, a piece of theoretical physics so beautiful and so profound that it's worth spending time just letting the concepts wash over you, even if the details remain mysterious. An instanton is a rare quantum event, a solution to the equations of quantum field theory that exists in what mathematicians call imaginary time, a concept that sounds like science fiction, but is perfectly well-defined mathematically. It describes the probability of a bubble spontaneously forming, of the vacuum tunneling from one state to another, from the false minimum we currently inhabit to the true minimum that might lie beneath it. These incidents are O4, symmetric, which means they're perfectly spherical in a four-dimensional space-time sense. They're Euclidean solutions, mathematical objects that bridge the false vacuum and the true vacuum like a tunnel through a mountain of energy. And the formula for calculating their probability factors in not just the quantum mechanics of the field itself, but also gravity's subtle influence. Because even gravity, even the curvature of space-time itself, bends and warps the quantum fields, affecting the likelihood of decay when a bubble nucleates. When an instant becomes real and a region of true vacuum appears in the sea of false vacuum, it maintains a spherical shape, not by design but by necessity. The field dynamics are isotropic, meaning they're the same in all directions. There's no preferred direction in space, no up or down or left or right, that would make the bubble expand faster, one way than another. So it expands uniformly, a perfect sphere growing at the speed of light, sweeping through space like ripples spreading across the surface of a pond. Except these ripples move at the cosmic speed limit and carry with them a fundamental transformation in the nature reality itself. Inside the bubble wall, scalar field dynamics create a thin layer of concentrated energy, a boundary region where the Higgs field is transitioning from its false vacuum value to its true vacuum value. This wall is where the transformation happens, where the laws of physics are actively being rewritten as the bubble expands. The wall itself rewrites the laws of physics as it sweeps forward, changing particle masses, altering force strengths, reconfiguring the fundamental constants that determine how matter behaves. The interior of the bubble features an inverted Higgs potential, a configuration where particle interactions flip from what we're used to. Attractive forces might become repulsive. Electrons might lose their mass entirely, unable to form stable atoms. The strong nuclear force that binds quarks into protons and neutrons might change strength, making nuclei unstable, causing them to fly apart or collapse together. Atoms, molecules, all the intricate structures built from quantum mechanics and electromagnetism, all of it becomes impossible in this new regime. As the bubble wall rushes through space at the speed of light, it leaves behind topological defects, features in the fabric of space-time itself that mark the transition from old physics to new. These are called Kibble-Zurek defects, named after the physicists who first described them. They're cosmic strings formed during rapid symmetry breaking, like cracks in the fabric of space-time marking the boundary between the old regime and the new, between the physics we know and the physics of the true vacuum. Domain walls separate the phases, regions where the field hasn't quite settled into its new configuration, where it's still transitioning, still finding its way to the true minimum. These walls are laced with tangled energy and broken symmetries, remnants of the phase transition that will slowly dissipate as the field relaxes into its new state. The bubble interior hosts scalar condensates, configurations of field that amplify the vacuum energy release exponentially, feeding on themselves, growing stronger as they expand, until the entire region has been transformed from false vacuum to true. The decay probability rises slightly near high-energy events, places where cosmic rays collide in the upper atmosphere, or where particles smash together in accelerators like the Large Hadron Collider. These high-energy collisions momentarily probe the structure of the vacuum at extreme energies, potentially creating conditions where tunneling is more likely. But the increase in probability is negligible, vanishingly small compared to the already tiny baseline probability. The energy barriers are simply too high, the tunneling too rare, for us to ever observe it happening in a laboratory or for cosmic ray collisions to pose any real danger of nucleating a vacuum decay bubble. Temperature also plays a role in the probability of decay. In the hot early universe, when the cosmos was filled with a dense, energetic soup of particles and radiation, thermal energy actually suppressed tunneling. The particles were bouncing around too quickly, too energetically, for the delicate quantum process of tunneling to take hold. The system was too hot, too chaotic, for the field to settle down and explore the possibility of tunneling to a lower energy state. This thermal suppression bought the universe time after the Big Bang, time for it to cool, to expand, to evolve into the state we see today. If vacuum decay had been likely in those earliest, hottest moments, the universe might never have made it to the point where stars could form, where galaxies could coalesce, where planets could develop and life could emerge. But the temperature was high enough, the thermal energy great enough, to stabilize the vacuum during those critical early moments, allowing the universe to pass through that dangerous period and settle into a state where vacuum decay, while still possible, is fantastically unlikely on any time scale we need to worry about. As the universe cooled and expanded, as the temperature dropped from the unimaginable heat of the first moments to the frigid 2.7 Kelvin of the cosmic microwave background that bathes all of space today, the probability of vacuum decay gradually changed, settling into a regime we're in now, where the universe is cold enough that thermal fluctuations no longer suppress tunneling. But the energy barriers are high enough that tunneling remains extraordinarily rare. The Coleman-de Lucia calculation takes all of this into account, integrating over all possible bubble configurations, summing over all the ways the field could tunnel from false vacuum to true, weighting each possibility by its probability, and arriving at a final number that represents the expected rate of vacuum decay per unit volume of space per unit time. That number is staggeringly small. So small that even if you took all the space in the observable universe and all the time since the Big Bang and multiplied them together, the expected number of decay events would still be far less than 1. But staggeringly small is not 0, and over the truly vast timescales of cosmology, over the trillions upon trillions of years that the universe might exist into the future, even staggeringly small probabilities eventually become relevant. The universe has time, endless time, more time than we can comprehend, and in that expanse of temporal infinity, the improbable becomes inevitable, the rare becomes common, and eventually, perhaps, vacuum decay will occur somewhere, sometime, transforming some region of space into true vacuum and beginning to cascade that might one day consume everything. But that day, if it comes at all, is so far in the future that it might as well be never. The time scales involved are longer than the time it would take for every black hole in the universe to evaporate through Hawking radiation, longer than the time it would take for protons themselves to decay if they're unstable, longer than the time it would take for the universe to expand so much that every galaxy outside our local cluster has been pushed beyond our cosmic horizon by the accelerating expansion of space. Vacuum decay, if it happens, will happen in a future so distant that the universe we see today will be unrecognizable, transformed by entropy and expansion into a cold, dark, nearly empty expanse where the remnants of today's stars have long since faded away. What determines whether our vacuum is truly stable or merely metastable? The answer lies in the masses of fundamental particles, particularly the Higgs boson and the top quark. These two particles, through their masses and how they interact with the Higgs field, shape the curvature of the Higgs potential, determining whether that Mexican hat shape has a true minimum deeper than the false minimum we currently inhabit, or whether the value we're in really is the lowest point, the most stable configuration the field can achieve. Precise measurements at the Large Hadron Collider have refined our understanding enormously over the past decade or so. Scientists have weighed the Higgs boson to incredible accuracy, determined the mass of the top quark to within fractions of percent, measured coupling constants and interaction strengths with unprecedented precision. And from all this data, they've constructed increasingly detailed maps of the Higgs potential, calculating how its energy varies as you move through different possible values of the field. The energy barrier height depends crucially on these measured values. If the Higgs were just a bit heavier or the top quark just a bit lighter, the potential might look completely different. The barrier between our false minimum and the possible true minimum might be higher, making tunneling even more improbable than it already is, or the true minimum might not exist at all, making our vacuum absolutely stable rather than merely metastable, but with the values we actually measure in nature. The calculation suggests we sit precariously near the edge, in a regime where the vacuum is stable enough to have lasted billions of years, but not obviously stable enough to last forever. The top quark is particularly special in this story. It has the largest Yukawa coupling of any known particle, meaning it interacts more strongly with the Higgs field than anything else. This strong coupling drags the Higgs potential downward at high field values, creating the possibility of that deeper valley, that true minimum lurking below where we currently rest. Without the top quark's heavy mass and strong coupling, the potential might look entirely different, might not have a metastable false minimum at all, might be completely stable, or might be so unstable that the universe would have decayed almost immediately after the Big Bang. The metastability parameter, derived from the Higgs self-coupling and the other parameters of the Standard Model, sits right at a boundary between stability and instability. Not quite stable, not quite unstable, but balance on a knife's edge in parameter space. This balance is remarkable when you think about it. Why should the universe's vacuum be right on the edge of stability? Why not clearly stable or clearly unstable? Some physicists have speculated that this near criticality might be telling us something deep about the nature of reality, perhaps pointing to new physics beyond the standard model that we haven't discovered yet, or perhaps indicating some kind of anthropic selection where only universes with vacuum near the edge of stability can support complex structures and observers like us. Fermion masses affect the vacuum stability indirectly through what are called quantum loop corrections. In quantum field theory, particles don't just interact directly. They also interact through virtual processes, ephemeral events where particles pop in and out of existence, borrowing energy from the vacuum for the briefest instant before annihilating back into the field. Each of these virtual processes contributes a tiny adjustment to the effective energy of the Higgs field. And when you sum over all possible virtual processes, you get corrections to the potential that can shift the location and depth of the false and true minima. Radiative corrections from electroweak loops fine-tune potential in subtle ways. They adjust the depth of the false minimum, sometimes stabilizing it a bit, sometimes destabilizing it a bit, depending on the exact masses and coupling constants involved. The mathematics of these loop corrections is incredibly intricate, involving integrals over all possible momenta, sums over all possible virtual particle configurations, renormalization procedures to remove infinities, and careful regularization schemes to make the calculations meaningful. But the result is a more accurate picture of the Higgs potential, one that includes not just the classical tree-level contribution, but all the quantum mechanical subtleties that arise when you take the full theory into account. In the early universe, electroweak symmetry restoration at high temperatures provided a natural protection mechanism for the vacuum. When the universe was hot enough, the thermal energy changed the shape of potential temporarily, eliminating the false minimum and making vacuum decay impossible during that epoch. As the universe cooled and the electroweak phase transition occurred, the potential took on its current shape, and the metastability we worry about today became relevant. But by then the universe had already expanded enormously, diluting any would-be nucleation sites and making the probability of decay in those early moments vanishingly small. Extensions to the standard model offer new possibilities for understanding vacuum stability. Two Higgs doublet models introduce additional scalar particles beyond the single Higgs we've discovered. These extra fields, with their own charge loops and couplings of matter, can deepen or shallow the potential barrier between false and true vacua, potentially stabilizing the vacuum or making it more metastable, depending on the specific parameters of the extended model. Composite Higgs scenarios, where the Higgs isn't an elementary particle but is instead made of smaller constituents bound together by some new strong force, connect vacuum stability to the dynamics of these new interactions at higher energies, potentially solving the metastability problem through technicolor or other strong dynamics. Supersymmetry, that beautiful symmetry between bosons and fermions where each particle has a superpartner with the opposite statistics, could extend the vacuum's lifetime significantly. In supersymmetric theories, The contributions from bosons and fermions to the loop corrections tend to cancel, stabilizing potential and preventing the runaway effects that lead to metastability in the standard model. If supersymmetry exists in nature, even if it's broken at energies above what we can currently probe, its effects might be enough to make our vacuum stable rather than metastable, ensuring that the universe will never decay no matter how long we wait. The seesaw mechanism, which explains why neutrinos have such tiny masses compared to other fermions, might also play a role in vacuum stability. Heavy right-handed neutrinos at very high energies could introduce new terms into the Higgs potential, terms that depend on these heavy masses and their couplings to the standard model fields. These seesaw-stabilized vacua could be resistant to premature tunneling, with the heavy neutrino sector providing an additional energy barrier that makes decay even less likely than standard calculations suggest. In string theory, moduli fields arise naturally from the compactification of extra dimensions. These moduli, describing the size and shape of the compactified dimensions, can interact with the Higgs field through non-perturbative effects, potentially stabilizing its vacuum expectation value. Kähler moduli stabilization in flux compactifications, where flux is threading the extra dimensions create an effective potential for moduli, can anchor the Higgs against radiative runaway effects, preventing the field from sliding uncontrollably toward decay and ensuring the vacuum remains in its current metastable state for timescales that dwarf even the cosmological timescales we've been discussing. All of these theoretical possibilities represent ways that physics beyond the standard model might resolve the metastability problem, might explain why our vacuum has lasted so long despite apparently being only marginally stable. But we don't yet know if any of these extensions are realized in nature. The standard model as we currently understand it, with just the particles and fields we've discovered so far, predicts metastability, predicts that eventual decay is possible if not probable. And until we discover new physics that changes this picture, we're left with the conclusion that the universe we inhabit is temporary, perched in a false minimum, waiting for the day when quantum mechanics allows it to tunnel to something more stable and different and alien. But again, the time scales are so vast that this conclusion, while profound philosophically, has no practical import for our lives or even for the future of our species over any reasonable time frame. The universe is metastable, but it's metastable enough to last far longer than we can meaningfully comprehend, far longer than the time it takes for stars to burn out and galaxies to fade, and even black holes to evaporate into the void. The metastability is a feature of the mathematical landscape we inhabit, a property of the equations that govern reality at its deepest level, but it's not something that will affect us or anything we care about in any foreseeable future. How long might our vacuum survive? Current estimates place the lifetime at over 10 to the 65th power years. Let that number sink in for a moment. 10 with 65 zeros after it. A 1 followed by 65 zeros. To put this in perspective, the universe itself has existed for only about 14 billion years, which is 10 to the 10th power years. The age of the universe, from the Big Bang to now, is a tiny fraction of the estimated lifetime of the vacuum, a mere blip in the vast expanse of time that the universe might persist in its current state. If you tried to write out the vacuum's lifetime in years without using scientific notation, the number will be longer than all the books ever written combined. It would take more digits to express than there are atoms in the observable universe. It's a number so large that it becomes abstract, losing any connection to our intuitive sense of time, becoming merely a symbol of vastness, of near eternity, of a duration so long that calling it forever is barely an exaggeration for any practical purpose. The lifetime of our vacuum is so vastly longer than the current age of the universe that it renders the threat beautifully abstract, remote, almost comforting in its distance. This is not something that will happen tomorrow or next year or in 1,000,000 years or even in 1,000,000,000,000,000 years. This is something that might happen, if it happens at all, in a future so distant that the very concept of future loses meaning, when the universe has expanded so much that every galaxy outside our local group has been pushed beyond our horizon, when every star is burned out, when every black hole has evaporated, when the universe is cold and dark and nearly empty, approaching the heat death that thermodynamics predicts for all closed systems. Gravity plays a stabilizing role in this story. The tiny energy differences between the false vacuum and the true vacuum create gravitational effects, subtle influences on the curvature of space-time that act like a gentle hand holding the ball in the groove of that Mexican hat potential. The energy required to overcome this gravitational barrier is enormous, far beyond anything we encounter in normal cosmic events. Even the violent explosions of supernovae, even the catastrophic collisions of neutron stars, even the accretion onto supermassive black holes at the centers of galaxies, none of these events comes close to providing enough energy to significantly increase the probability of vacuum decay. Black holes themselves might nucleate bubbles. Their extreme densities and warped space-time create conditions unlike anywhere else in the universe. Regions where the fabric of reality is stretched and stressed to its limits. But interestingly, spinning black holes, those with significant angular momentum, might actually stabilize the vacuum rather than destabilize it. Their rotation, their ergosphere, the way they drag space-time around with them as they spin, all of this creates conditions that suppress bubble nucleation rather than enhance it. So even black holes, those cosmic monsters that devour everything that falls too close, might paradoxically be helping preserve the universe rather than destroy it. In the early universe, primordial black holes, if they were abundant, would have posed the highest risk for seeding decay bubbles. These tiny black holes, forming in the first moments after the Big Bang from overdensities in primordial plasma, would have had extreme densities and could have created temporary hot spots where vacuum decay was more likely. But we're still here. The universe didn't decay in those earliest moments, which suggests either that primordial black holes were rare, too rare to significantly increase the decay probability, or that the vacuum was more stable than we thought, robust enough to survive even those extreme conditions. Neutron stars pack immense density into a sphere just a few miles across, squeezing more than a mass of our sun into a volume the size of a city. This extreme density amplifies local field fluctuations, creating situations where the Higgs field is compressed and stressed in ways that don't happen anywhere else in the current universe. These could be weak nucleation sites, places where the barrier to tunneling is slightly lower than average. But even these extreme objects, with their incredible densities and bizarre physics, seem insufficient to trigger vacuum decay. The universe has been making neutron stars for billions of years, and none of them has nucleated decay bubble yet. Magnetars take the extremity even further. These neutron stars have magnetic fields 1 trillion times stronger than Earth's, fields so strong that they warp the quantum vacuum itself, affecting how virtual particles pop in and out of existence in the space around them. These colossal magnetic fields can warp the local Higgs vacuum expectation value, creating fleeting high-risk zones where the field is temporarily displaced from its normal value. But even these zones, as extreme as they are, seem unable to push the vacuum over the edge into decay. The universe continues undisturbed, stable in its metastable state, patient in its existence. Quasar jets punch through space-time with their incredible energy, accelerating particles to velocities so close to the speed of light that they carry nearly all the energy they could possibly have. These jets momentarily spike local nucleation probabilities, creating temporary conditions of extreme energy density. Cosmic voids, ironically, the vast empty regions between galaxy clusters where almost nothing exists, might also offer higher nucleation probabilities per unit volume. With lower particle density, there are fewer interactions to stabilize the vacuum, less noise to suppress quantum events, potentially making these empty regions more susceptible to decay than the dense regions where galaxies cluster. Yet across billions of years, across countless galaxies, across voids and filaments and walls in the cosmic web, across neutron stars and magnetars and quasar jets, and all the violent astrophysical phenomena the universe produces, the vacuum holds. It remains in its metastable state, unchanged, persistent, patient. This persistence is itself remarkable, a testament to just how high the energy barriers really are, how improbable vacuum decay truly is, even in the most extreme environments we know of. And so we drift here at the end of this long journey through the science of vacuum decay, having explored the invisible ocean of the Higgs field, the quantum tunneling that might one day transform everything, the delicate balance of particle masses that determines whether our universe is stable or metastable, the vast timescales over which decay might occur. We've contemplated the end of everything in the most abstract sense, thought about what it means for the universe itself to be temporary. Consider how even the laws of physics might change if that decay ever comes. But in contemplating this cosmic ending, we found not fear but peace. Because if even the universe is temporary, if even the laws of physics are subject to change, then our own troubles are revealed to be what they truly are: fleeting, temporary, beautifully insignificant in the grand scheme of things. We can let them go. We can release our grip on our worries and anxieties and fears, let them dissolve into the quiet darkness, and simply rest here in this moment, In this universe that has been stable for billions of years and will likely be stable for billions more, in this brief window of cosmic time when matter can organize itself into complex patterns, when stars can shine and planets can form and life can emerge and contemplate its own existence. Rest well, sleepy soul, wherever you are. Let the vast timescales of the universe cradle you. Let the knowledge that all things are temporary give you permission to release your grip on everything. Let the invisible ocean of the Higgs Field, permeating all space, remind you that you are part of something vast and ancient and beautiful. Tomorrow the cosmos will still be here, patient and quiet and immense, continuing its slow drift through time, carrying us all toward whatever future awaits, whether that's transformation or continuation or something we haven't even imagined yet. The universe continues its slow, patient tick. The stars still shine. The galaxies still turn. And for now, for this moment, for this beautiful, fleeting, eternal now, everything is exactly as it should be. Let your breathing slow. Let your thoughts quiet. Let yourself drift into the darkness, into rest, into the peaceful knowledge of the universe, vast and mysterious and temporary though it may be, is home to this moment of quiet contemplation, this gentle surrender to sleep, this recognition that we are all part of something infinitely larger than ourselves. And with that thought, let yourself go. Let consciousness fade. Let the scientific details blur and merge with dreams. Let the universe, in all its metastable glory, hold you gently as you drift away. Rest now. Tomorrow will come. But for now, there is only this. The quiet, the darkness, the soft ambient drone of existence itself, carrying you gently into sleep.